All right, thank you everyone for coming back. So my name is Sopheak. I am a postdoctoral researcher at the Karlsruhe Institute of Technology. It's still in Germany. It's Karlsruhe. It's like midway between here and Stuttgart. Yeah. So if you want, you can drop by KIT in the future. So I made some changes in the title. So instead of magnetic skyrmion and magnetic Hopfions, as well as their dynamics, I'm switching to this nonlinear Hall effect from magnetic octopoles instead, maybe because of the interest for both the theory and the experiment. So let's begin then. So this talk is based on a completed project which was done in collaboration with a friend of mine, Dr. Adarsh Patri, who is now based at MIT. It's available on the archive right at the moment. It's being reviewed. So let's begin with the linear version of the Hall effect before talking about the nonlinear Hall response. So as you may all know very well already, that the Hall effect is a phenomenon where a transverse Hall voltage is developed upon applying a longitudinal current across a system. It is characterized by the conductivity tensor at the linear order of the response function. It's just a rank 2 tensor, sigma A and B. It describes how much the current is obtained by applying the electric field on the system. Phenomenologically, the Hall effect has been introduced as coming from various physical origins, including the Lorentz force. It's just the classical physics, how the electron experienced the Lorentz force in the presence of an external applied magnetic field. You can also have contribution from the intrinsic properties of the band structure. You probably heard about this already. It's just the Berry curvature physics. And finally, we also have contribution from the impurity scattering. And the main focus of today's talk is the intrinsic effect coming from the non-trivial topological features of the band structure. Yeah, and this has been can be seen immediately from the semi-classical consideration. If you look at the equation of motion of an electron wave packet, you will see that the velocity of the electron wave packet, which is this time derivative of some position quantity, it is given by the group velocity, but in the presence of the electric field, there is a modification coming from some sort of an internal magnetic field known as the Berry curvature. Yeah? And this is the force equation where the time rate of change of the momentum is proportional to the electric force, right? And if you plug into the Boltzmann formalism, you will find out that the Hall response tensor sigma AB, denoted by this superscript H, is proportional to the summation over all the contribution of the local Berry curvature from all the occupied state. Yeah? And this is the formula for the Berry curvature. It has a very analogous form as in the Maxwell equation, where it is expressed as a curl of a vector potential, but instead of a real space, this is the reciprocal space. Yeah? And this vector potential is related to the Bloch wave function in this fashion, where here is the gradient in the reciprocal space. So we will analyze why this written in this form give us a lot of insights into the physical consideration. So there is a relation with the topology if you view the Berry curvature as a curl of some vector potential, because in the insulator you need to sum over the contribution from entire band. Yeah? And the band extends over the entire Brillouin zone. In 2 dimensions, the Brillouin zone is a torus. And it is known that if you try to define the vector potential on a torus, you cannot do that smoothly. There is always a singular behavior which translates into the fact that you have a non-trivial topology in the system. So if you really do it properly, you will find out that if you sum over the entire torus, you do not always get 0. You can also get cases where this is just an integer, which is the famous Chern number. Yeah? But in this talk, we are interested in the relation with the symmetry. Yeah? So as you can see, this can be viewed as some sort of a net effective magnetic field. So I can express this loosely as some, I can call it an order parameter, which is denoted by a 3-component vector M, which is, you can call it the Hall vector, and it has the exact same property of the effective magnetic field, including that it breaks the time reversal, and it is also an axial vector, meaning that if you perform a inversion symmetry, this one is protected. It does not change sign or anything like that. So from this, we can learn that in a system, if you have an order parameter which has this property, it immediately implies an activation of a net Berry curvature in the system. Yeah? So if your system have a certain symmetry condition such that this order parameter is allowed, I would expect the anomalous Hall to be present. And if the symmetry is so strong that this guy is forbidden, then I do not expect any anomalous Hall in the system. Yeah? So let's see some example. In the ferromagnet, this order parameter is nothing but the magnetization. Yeah? And that would inspire the usual phenomenological or empirical relation between the magnetization and the Hall response coming from the Berry curvature of the system. However, in the past 2 decades or so, there were a lot of attention putting into trying to find out how to activate the Berry curvature in antiferromagnets instead. Yeah? And the design is that instead of having a direct magnetization, you can have a very complicated magnetic order in combination with some very low crystal properties that eventually allows this order parameter to survive. So you can end up with a very large anomalous Hall effect. However, the magnetization can be very, very minuscule. Yeah? So the example would be this very famous manganese 3X compound, where if you analyze the symmetry of the magnetic, in this compound, the manganese atoms, which are the orange dots, they are the magnetic moments in the system, and they ordered in this 120-degree type of structure. And if you do the symmetry analysis combined with the non-magnetic iridium atoms, you will find out that there is a symmetry allowed order parameter M that point along the 111 direction of the system, and you will get a non-trivial anomalous Hall effect even though the magnetization is very small. Yeah? This also inspired in the collinear case, where this leads to the emergent field of the altermagnets. So this is the ruthenium dioxide, which is an altermagnetic candidate. So in the system, you can have 2 sublattices A and B, where the two sublattices, they realize the Neal order. Yeah? And the Neal order is potentially collinear. And if the Neal order point along the X direction in this compound combined with the low symmetry of the crystal, you can check that there is this order parameter that point in this 001 direction of the crystal. Hence, I also expect the anomalous Hall to be present, even though the magnetization is small. Yeah? So in this talk, we are interested in asking the question, so what if we have a symmetry condition such that such a magnetic dipole-like order parameter M is completely forbidden? So what happened to the Hall effect in the system? Yeah. And the obvious answer is that the Hall effect will vanish. But is that just a boring statement, or is there some other interesting effect in the system? Of course, if the linear order vanishes, then the nonlinear effect becomes important again. Yeah? And here I'm going to show an example where this nonlinear Hall response can be used as a signature to detect some exotic ordering, yep, which is the magnetic octopolar ordering. So the outline of this talk is to talk about this magnetic octopolar ordering in a platform of heavy fermion compounds, and talk about how this how the octopolar order can give rise to very interesting band structure that supports the Berry curvature quadrupole, and as the result, this leads to the signature third order Hall effect in the system. And I will talk about some aspect of the Hall effect and move on to give some other example beyond just the ramp of the heavy fermion compounds. Yeah. So let's begin. So this is the system where I take as an example to study all of this interesting phenomena, which is a heavy fermion system. It is this so-called praseodymium 1 to 20 family of compounds. So here are two examples where we can have iridium atoms or zinc, and the zinc can be viewed as this green balls that form a very high symmetry cage surrounding the praseodymium atom. And if you are doing the atomic physics, you find out that the chemistry of the praseodymium compound is the praseodymium 3+ ion, and the relevant physics is controlled by the F electron. It's the electron in the 4f orbital of the system. And we do have not just one, but two F electron. And if you analyze the effect of the interaction as well as the strong spin-orbit coupling, you will find out that these two F electron will form a total angular momentum J equal to 4 subspace. J equal to 4 implies that you have 2 times 4 plus 1 equal to 9 degeneracy, right? It's from quantum mechanics. However, in the presence of the crystal field environment given by the green atoms, this 9-fold degeneracy is further split into various subspaces. One of them is called the so-called gamma 3 subspace, which has 2 degeneracy. This is a doublet. Yeah? So a doublet is more interesting than a singlet. A singlet is boring. So a doublet, there could be something going on. So what you can show is that this doublet quench the dipole moment in the system. Yeah? So you do not have the boring dipole moment in this system. So you can check it explicitly by looking at the matrix element of the angular momentum operator, and you find out that within this 2x2 matrix, you get identically 0. So the physics is now dominated by higher moments in the system, which include the charged quadrupole moments, which are characterized by this type of operator where J, X, and J, Y's are the angular momentum operator. But in this talk, we are not interested in this. We're interested in this magnetic octopole moment, which involve, instead of 2, it's the 3 angular momentum operators. And if you have 3, if you have a cubic function of angular momentum which break the time reversal, obviously this is magnetic because it is odd under the time reversal. Yeah? So here it's even under the time reversal because it consists of 2 angular momentum operators. Yeah. So this is the atomic physics. So at every single site, this system is very promising to stabilize octopole moment. If you put it back into the solid state environment, the crystal environment, these octopolar moments can order ferroically. So you have a ferroic ordering of the octopole moments in the system, which is going to have this type of symmetry in the system. It is odd under time reversal, and it is even under the inversion because the angular momentum does not care about the inversion symmetry. Okay, and as I said, it is possible to develop a long-range ferroic ordering of this object. Yeah. However, it's very hard to detect. Yeah. All the conventional ways to probe the dipole physics is out of the window, including the neutron scattering because they interact very weakly, or if not at all, 0, or other probes. So the challenge is really how to probe this type of magnetic orders. And in the past, there were proposals by using some sort of indirect coupling between this order parameter, the strain, and the applied magnetic field in the system. But here we are proposing something simpler, which is to use transport to detect this type of ordering, yeah? Which is going to be the subject of the second part, so from this octopolar ordering to the third order Hall effect. So to really see this, I consider a simple tie binding model, which consists of conduction electron floating around in the cubic environment, yeah? And on every single side of this cubic crystal, there is an octopole sitting there, yeah? And then we consider the interaction between the conduction electron and the octopole moment in the system, which is captured by this tie binding Hamiltonian, where H0 it just describes the hopping of the EG electron in the crystal, and the coupling between the octopolar order parameter phi and the conduction electron is achieved in this H phi term. Yeah? The entire system, when I consider this, we can study the band structure. So here is the band structure without and with the octopolar ordering. So without the octopolar ordering, you can see there are some degenerate, some band which become degenerate, and they are usually protected by symmetries. And the answer is that they are protected by some mirror and C3 symmetry, which are broken the moment the system enters the ordered state. So when the system enters the ordered state, these band sticking are now, the degeneracy are now lifted like this, as you can see, and these give rise to a very strong local Berry curvature around this band crossing point. Yeah. Not only that, if you look at the Brillouin zone and you consider only the xy plane, meaning that setting kz to 0, you will see that the Berry curvature distribution of the electronic bands has this structure. So in some region, it has strongly negative sign of the Berry curvature. Some region it is positive, but the sign changing is such that it exhibits some sort of a quadrupolar structure in the system, changing sign 4 times. Yeah? Obviously, if you do the summation of the Berry curvature over the occupied state, you will see that you get a 0 because you don't have monopole structure, you have quadrupole structure. And surprisingly, not surprisingly actually, if you compute this Berry curvature quadrupole, which is defined by, instead of summing over just the Berry curvature, you take the momentum space derivative, you will find a non-zero value of this QABC Berry curvature quadrupole. And in the next few slides, I will tell you that this is directly going to enter the formula for the Hall conductivity, but not for the linear response. It is instead for the third order response. Yeah? And the third order response bear 4 indices because now you have to relate 1 vector to 3 vectors. So you need 4 indices to allow them to talk to each other. So, so the formalism that I use is just Boltzmann equation, which describe how describe the time dependence of the Fermi distribution function in the non-equilibrium setting, where we assume some phenomenological relaxation time approximation, where this is the non-equilibrium distribution function and this is the equilibrium distribution function. And we solve this Boltzmann equation together with the semi-classical equation of motion for electron and do the expansion term by term in the power of the electric field. What we find out is that beyond the linear order, you can talk about the second order first. In the frequency space, the current is described by a rank 3 tensor. This is the second order conductivity. And it can have 2 possibilities. Either you can have second harmonic generation, or you can have 0 frequency, even though you are driving the system at a non-zero frequency. Yeah? And the second harmonic generation can be split into a Drude term, which we don't care, and a Hall term, which is proportional to this famous Berry curvature dipole. So if we have just one derivative, it's just a dipole, we will see that we will have 2 derivatives when we talk about the third order conductivity. However, this second order conductivity is not relevant in our system because in order to activate the second order, one needs to have a broken inversion symmetry. Yeah? You can do this quick check. However, I just want to highlight how one can measure this system, this type of second order Hall effect. It was done before in the WT2. So what they did is to consider various experiment very simple, similar to the usual Hall measurement, applying current between the LED number 7 and 8, and then measure the Hall voltage drop between the LED 3 and 4. Yeah. However, we do not. They did not measure the Hall voltage at the omega frequency. They measured it at the 2 omega frequency, and they found out a very nice quadratic relation between the amplitude of the second harmonic generation in the Hall channel versus the applied current. So in the third order Hall effect, one would expect this to be a cubic function instead of a quadratic. Yeah. As I said, the second order not relevant to our case because of the presence of the inversion symmetry. So let's go to the third order Hall effect. So if you do the same, if you play the same game, you will find out indeed that the third order response it have, instead of a second harmonic generation, it is a third harmonic generation, and it is related to the double derivative of the Berry curvature and then integrated over all the occupied states. Yeah. So let's look at some aspect of this third order Hall effect. Well, it is very anisotropic. It depends on how you do the measurement. Yeah. So you now, when you think about Hall effect, you think about the Hall plane. Yeah. Hall plane, which is defined by the applied electric field and the Hall current. Yeah. And usually in the Hall measurement, the third direction is the magnetic field. But in this case, we don't have. So if you think about the relative position between the applied electric field and the measured current, the developed Hall current, one can map out by viewing in the Ex, Ey, and Ez space that I apply the electric field in some direction. The Hall response is going to be perpendicular to this electric field, so it lives in this as a tangent vector on this sphere. Yeah. So if you map out all possible direction of the electric field, you will get this structure. If you decided to choose your system to be in the XY plane, you will see that you can vary the electric field, direction of electric field in the equatorial plane. And this would be, the blue arrow would be the direction of the Hall response together with their magnitude given by the size of the arrow. So you can see that in some cases when the electric field point along a very high symmetry direction, you get 0 Hall signal. But for example, if you apply the electric field along this direction, you get a very big Hall signal. Yeah. Okay, it also depends on where your chemical potential is. For example, here, if I put my chemical potential near this avoided band crossing, you will see a very huge signal in the Berry curvature quadrupole. And if you put it somewhere unluckily, then you will get weaker signal. It also depends on the order parameter in a very strange way. So the Berry curvature quadrupole plotted as a function of the order parameter becomes very singular when the order parameter is very small. Simply because when the order parameter is very small, you have a very concentrated Berry curvature, local Berry curvature, and then you take its derivative. Yeah. So taking derivative of a singular object, you will get some big response. So we propose actually the whole experiment to detect this hidden object, which is usually hard to detect in the conventional probe. This is very similar to what I showed earlier, just applied a sinusoidal current and then measure the third harmonic generation of the Hall voltage, and then try to hunt down some cubic relation between the amplitude of the current and the Hall voltage. Also remember that we have a very anisotropic feature together with a very non-universal dependence on the order parameters. We also estimate the strength of the Berry curvature quadrupole in this praseodymium 1,2,20 compounds. We found that this is actually quite big. It is comparable to the Berry curvature quadrupole, which was estimated in this iron tin compounds where the third order Hall effect was measured. So that might be a very good sign. Do we have time? 2 minutes? Okay, so maybe I'll spend the last 2 minutes talking about other systems that also realize the third order Hall effect. It is the famous alter-magnetic candidates, especially those that are the so-called D-wave compounds, D-wave alter magnets. So for example, if we take this ruthenium dioxide consideration again, and instead of having the needle vector point in the xy plane, we consider the needle vector point along a very high symmetry direction, along the 0, 0, 1 direction, which I saw in the literature that this could even be the ground state of the ruthenium dioxide, so you don't need to do anything. It's there, and the anomalous Hall turns out to be no, because if you look at, there is some symmetry that forbids the linear Hall effect from happening. So the answer is that the third order Hall effect will become the most relevant signal in the Hall measurement. And this is actually not very new. It's not a news. It's actually was already studied in this arXiv article from the end of 2023. So as I mentioned, it turns out that this type of setup also realized a magnetic octopole, but it is a different type of octopole. This is probably related to the so-called cluster octopolar ordering, while in our case, it is the atomic octopole ordering. We don't need any cluster. Well, with that, that's the end of the talk. So I actually propose to have a Hall measurement to identify a very hidden ordering, which has been very mysterious for the heavy fermion community for a very long time. So a third order Hall effect might be the answer. And third order Hall effect should also be seen in other systems, including the D-wave alter-magnet, where the leading order are suppressed by the symmetry. And the outlook for this is, of course, the experimental realization of our proposal, followed by more quantitative estimate, taking into account of all other microscopic contribution to the third order Hall effect. We know that we have impurity and so on, so what are the role of the impurity and so on into this? So in order to have a quantitative study, one is to take into account a lot of details, and so probably some qualitative understanding of the third order Hall effect beyond the semi-classical formalism is also needed. With that, thank you for your attention.